After the tone, please state followed by the pound sign.
Your line has been muted.
All the attendees, apparently this webinar just is not going to work out. John, you have controls if you want to go ahead and go for it.
What a day. All right, so it snows a half an inch in Washington and nothing works. My apologies. So let's go ahead and get started. It looks like we have a lot of folks that have put in the time this afternoon. Again, I apologize for the technical issues. I was in a constant do-loop with downloading WebEx software, but Jacqueline asked us to put together an overview of high-resolution tools and how they can be employed, and we employ them to really try to put a control around LNAPL management on sites. And so we've loaded what I would call a gargantuan-sized presentation here and scheduled for a couple of hours. It's pretty hard to do this and not be too interactive, so maybe Jacqueline can break in if we get questions and things as we go along. I'm not sure what you told them about questions, Jacqueline, but I'm going to kind of proceed down the path, giving you an overview of these tools, how we use them on these types of sites, talk about different tools, and as we go along, we'll hopefully generate some thoughts and some juices flowing as we go along. So, just kind of a reminder of all of our mission is that we all live on this planet together, and our goal is to try to sustain that as long as possible. And so we really try to look at how can we collect the best information, expend the least resources, and sustain what's going on. So just kind of a reminder of that. And so we tend to look at these tools in how can we efficiently, sustainably address the social impact of where we are working, the economic impact, and obviously we're all focused on the environmental component of it. So I'd just like to kind of remind folks that's the business that we're all in. Unfortunately, over time we've let this sort of environmental restoration concept and market and rules and regulations really kind of grow into its own monster. So we're spending a lot of money every day, and unfortunately a lot of the information we have is really based on old science or old technologies and comes to us in a very incomplete, inaccurate, and really kind of late in the game to make our decisions. So we're really been trying to stress how can we get better information up front in order to make better decisions on the back end. I imagine most of you are familiar with the national tank studies that have been done and how we look at projects, but we end up in these very iterative, go out and collect the data, analyze the data, samples, send that back in, reports, questions, what about over here, what about this, what about that depth. We end up in a very long series of cycles that take a lot of time, and then they end up in a very expensive process. So what we're trying to say is how can we cut through this faster to get to a decision of management, which could be liability management, it could be it's time to do something in terms of restoration, or it may be, we can't spend the money it's going to the restoration methods that we're thinking about are really off target or aren't going to be supported by the data that we have. And if we tap into the history from U.S. EPA, they document fairly well in the studies they've done is 80% of the air goes into, essentially we've gotten the data from the wrong place. So it's been now almost 20 years, but within the last 10 years and certainly the last 5 years that this concept of high-resolution tools came about. How can we look at more data faster and more completely, both vertically and horizontally in our sites in order to collect better information and really understand the variations that go on in the subsurface. Our friends at Vista Geoscience out in Denver area are using a term they call remedial design characterization. They're in the business of doing remedial work, and when you talk to most any remedial provider, whether it be, the number one thing they're always complaining about is insufficient characterization. So the question is, how can we get better characterization, and what is in that? What kind of characterization do we need? Where is the mass? How much mass is it there? Is it waterborne? Is it in the soils? What are the physical and chemical parameters that are going to affect the type of remediation that we're going to employ? How long are we going to be dealing with this issue? What's the effect, the back diffusion effects? What are the delivery mechanisms in order to get to the depths that we need to? So how can we get better information to support these types of remedial designs? The other thing we learned a lot from the work being done by ITRC and the folks that are participating in that and the science is that we spend a lot of time looking at groundwater data. A lot of remedial designs are based on groundwater data, yet there's a massive difference between the contaminant load in the soils versus the groundwater. So how can we get better information about the soil structure, the soil loadings, so we can really get at the heart of the contaminants? And that's, again, what we're trying to focus on with this group of high-resolution tools. And in terms of correlation work, I'd like to make a point. We're talking about high-resolution tools, and that's more than just direct sensing tools. There's a lot of high-resolution sampling, both soil and groundwater sampling that can go on, can happen with microbial activities. All these pieces go together, and while direct sensing tools can do a lot of it, some of it still, much of the data still requires the high-resolution sampling and analysis approach. So you've got soils, groundwaters, we'll kind of skip to that. What that lends to us is, instead of sort of large brute force remedial methods, we can then get into a much higher resolution description on how to do remedial designs, whether that be injections, whether that be treatments, where we're going to place the hardware, where we're going to place the chemicals, where we're going to place the heat, or whatever happens to be our remedial activity. So we can get into much more refined, much more cost-effective, and much more technically effective results by using tools such as this. Okay. So that's kind of the background of what we're doing. This is a slide that basically says, with the direct sensing world, in the high-resolution world, we're able to drive sensors in the ground with any number of types of drilling systems and directly sense soil, water, chemical, physical parameters in high resolution, and that's generally about 20 times a foot is a rough number. And we're going to see that information immediately in the field and be able to get a feeling for what depths and what soil structures, what permeabilities, and what contaminants we're seeing within the first few hours of being on site. Most of that data is now in an digital format and can be moved, so we then can move that information through decision makers and do a number of types of analyses on that, and then get it back to the decision makers. And so instead of these long extended cycle times of information flow, what sensors allow us to do is essentially cut that cycle time down to minutes. So now we're starting to really start going after sites looking at a combination of much more data, thousands of times more data points or information points, and we're moving that information much faster due to the internet, due to the processing capabilities of the sensors. So now we're bringing decisionable data to the forefront earlier in the process, and that gives the technical team and the finance team, for that matter, better technical controls of what's going on and better financial budgetary controls and project management controls on what's going on. So we're really approaching this from a systems approach to end up with a higher definition, more accurate site conceptual model, and we do it in a much more real time. That's the background of sort of why high resolution and as it deploys. If we focus then in on this non-aqueous phase liquid, typically the title given to our oils and our petroleum products, then we open up a whole sort of the next chapter of conversation. I'm going to base a lot of what I'm presenting off of guidance that you can find with ITRC, which I encourage you to go through their LNAPL training program. You can do that online, or you can do it at one of the many workshops they have around the country. ASTM also addresses these issues, as well as the oil industry themselves address how to tackle this LNAPL challenge. I'm going to oversimplify it down to where's the oil, what's the issues with the soil, what's going on with the water, what are the microbial activities bugs doing for us, and do we have a vapor intrusion issue? So we're going to kind of look at that and say, well, how can the high-resolution tools help us address these issues? The oil question, I really like the way ITRC takes a look at this. You know, we all say, well, there's oil in the ground, we got to do something about it. Well, then the question is what are you going to do about it? So what do we really need to know? We need to know, where is the oil really? Have we stopped or secured or turned off or controlled any existing leakage, sources of oil, sources of contamination, sources of pressure when we get into the discussion about pore pressures and things of that sort? Now that we've done that, has the oil reached equilibrium, or is it still moving through the subsurface? In other words, is it leaving our site or our area of concern or our controlled area or whatever we want, or is it in fact pretty much reached equilibrium with the subsurface formation, and it's not, using ITRC's term, moving? So then the question is it mobile? Within the footprint of the remaining oil, is it mobile? Can we recover it? Is it transmissive? Can we suck on it and then actually recover it? And therefore, we ought to have skimmer systems out there or other types of recovery systems. And then you kind of walk back up that continuum. Then you get to the point, do we really have LNAPL? Or do we have dissolved phase? Or do we just have residual phase material that's not above saturation? And then the question, as we talked about earlier, is there a vapor issue? It's quite possible that the oil has reached equilibrium with the formation. It's confined within a footprint, and is in fact degrading faster than we can recover it, i.e. it's no longer of sufficient saturation levels that it's transmissive or recoverable, and we really ought to let the microbial activities do its job. Could we go in and dig? You know, we could dig and remove. That's really kind of moving the problem to another location, but it may be the appropriate thing to do depending on the business and technical goals for the site. So those are kind of oversimplifying the LNAPL questions about the oil. As hard as it is to believe that in 2015 we still have a fundamental misconception about what LNAPL does in the subsurface, and a lot of people still think we're in this LNAPL float. So we have oil floats on top of water, and the fact is that we have air, NAPL, water continuum or mixture like this, that's exactly what happens. So sitting on the desktop here, oil will float in my glass of water. But if we're going to take that into the subsurface and then start acting on that oil in the subsurface, we're going to get a different type of relationship. So we're going to find the oil under the water, we're going to find oil mixed on the soils, absorbed to the soils, mixed in the pore spaces, and we're going to have a lot of competition about what's going into that subsurface. So, again, courtesy of ITRC, let me just say it gets very complicated once we go underground and we remove that simple air NAPL water interface. And as I think all of us in the country and the globe, for that matter, have seen a lot of changes in our groundwater structures and resources here over the last several years. The fact that the water has moved up and down and formations have changed because of whatever reason, natural or man-made causes, we have now created even more complexity to where is the water-oil kinds of combinations that are down there. So, to the remediation guys, this is our horror story. So how do we deal with this? Where is the NAPL now? Where is the water now? Where is it moving? Where is it not moving? Where is it mobile? Where is it not mobile? So these are what we're going after. So we look at the soil challenge. 15, 20 years ago, it was a simple problem. The soils were permeable down to the clays, and then they were not permeable, and that's what the oil was probably, spreading out over. I will tell you now, over the last 3 to 5 years, I've sort of removed the concept of sands or clays or silty sands or sandy silts from my vocabulary, because what we really find is what we're interested in the environmental business and the recovery business is the soil permeable or is it not permeable? Will fluids move through the pore spaces or will they not move through the pore spaces? And if they won't move through the pore spaces, it really doesn't matter whether it's a sand or a clay. It's really the issue of permeability. So understanding, well, it behaves like a clay is one thing. The fact that it's not permeable is sort of the piece of the puzzle. I have a video scheduled in here because we've made computer swaps. We're not going to look at that right now, but I will reference it to the work that Professor Tom Sales was doing at Colorado State. A lot of excellent work being done on the LNAPL research there. If you go to his websites there, you can find some very interesting videos. One of them that addresses this issue of if we have this variability in the subsurface, what we're learning now is obviously we have different soils with different states of permeability, which makes them really different transport zones, or the opposite of that, they make them storage zones. And what the video will show you is very clearly, if you're applying contaminant, i.e. you have moving contaminant, and it's hitting these variable types of permeable soils, the non-permeables will tend to absorb and the contaminants will tend to adhere there. The permeable ones will essentially, I'll use the term, wash themselves out, but the contaminant will move on down gradient. And what we find is in those high permeable zones, it's very much like the interstate, not at rush hour. You can get very high speed, high transport numbers in very small portions of the subsurface. And if you're looking at a vertical transect or plane of that, there'll be a 10% hole in there where the mass flux is occurring. And then there'll be a whole lot of locations where it's not occurring, and the material will adhere to these tighter, lower permeability or tighter soils, and it will back diffuse off of that for days, weeks, and months afterwards. All right, so now we've added that complexity. So where's the permeability? Where's the storage? Where's the transport? So, okay, that opens then this concept of, well, if I put these transects in there, either with high-resolution tools or with my monitoring wells, assuming I get my monitoring well screens properly placed vertically in the right transport zones, then I can calculate a mass discharge rate going down gradient, and I can get out of the business of estimating, well, we had a petroleum release at point A, and we've got a water body down gradient X number of feet, miles, yards, whatever. And if I put that in my groundwater modeling program using average numbers, then I expect it's going to take X number of years for that discharge to reach the water body. Well, if you come back to the 10% concept, that's not going to be true because most of the transport's going to be occurring in that 10%. So finding that 10% with the high-resolution permeability measurements and chemical measurements is critical. The other side of that is if my screens are not in the right depth zones, if the screen is sitting in a low permeable zone and I'm calculating my groundwater transport off the low permeabilities, I'm going to then have very inaccurate information. So I'm going to kind of skip through that. So what we get now, looking at this very heterogeneous subsurface, we get from a very fuzzy picture, we get much more specific, granular information in higher power. Now, I think I've kind of hit this one hard enough. You know, we're going to have most of our mass, if it's moving, is going to be moving in a very small percentage of the geospatial volume. So what high resolution then becomes is essentially how do we tackle the geospatial challenge in a reliable enough manner to look at different types of compounds, different types of soils, and different types of permeabilities. This is a quick, sort of quick and dirty overview of the types of readily commercial available high-resolution systems. There are others that I don't have on the list that aren't as prominent. But in big picture, membrane interface probe has been around now almost 20-something years. It is a heated probe with a membrane that separates the subsurface from the internal gas flow, hence the name membrane interface. And it basically, the easiest way to think about it is a VOC tool. It's going to see everything that will volatilize above a certain temperature with a sufficient vapor pressure. And if you got the right detector on that, you're going to be able to say, well, I got a chlorinated versus petroleum, or I got methane versus chlorinated, or whatever. And you're going to see all three phases of contaminant: vapor phase, dissolve phase, and non-aqueous phase. Whatever I said. So that's the easiest way to think about MIP. It comes in lots of different varieties of detectors, heated trunk lines, low-level systems, different electrical conductivity versus hydraulic profiling combinations. So, 15 years ago it was a MIP. Today it's MIP, variations of 5 or 6 or 7 variations on that. The second item on this list is the family of laser-induced fluorescence tools. For the world of NAPLs and LNAPLs, this is an ideal tool for determining source area footprints and configurations. Uses a principle of, and we'll go more into this, but uses a principle of high-energy lasers working in the ultraviolet spectrum, about 308 nanometers, shoots a light out down a fiber optic out a sapphire window, and if there's a wayward petroleum molecule outside that window, it'll excite and fluoresce with a unique signature of its PAH structure, and we'll pick that signal back up a second fiber optic and take it up to the surface and do signal processing of that. You hear about these tools in the market. It's called UVOS, ultraviolet optical screening tool. ROST is the old rapid optical screening tool. HARGOS is a different frequency used for the heavier components, tar-type components. You see here something called a fuel fluorescence detector, which is not laser-based, but works on the same concept of fluorescence with a little less energy, a little less discrimination. So there's a family of those tools. The key here is you must have the residual petroleum present. So you think about it like a light switch. If it goes down and hits petroleum, it turns on. If there's no free-phase petroleum or residual-phase petroleum, you will not get a signal out of that. Excellent for tracking LNAPL spills. Hydraulic profiling tool, HPT, has been out there now for a little over a year and a half, 2 years. Excellent tool for really evaluating what's going on in these pore spaces, which soils are going to be permeable or allow for fluid flow, which ones are not. Similar tool, pneumatic slug testing, can be put on your existing wells and in the formation next to it, so you can do a comparison. Is my well really reacting or performing to my subsurface as my is the subsurface in the well giving me the same information? Electrical conductivity or soil resistivity has been around for decades. It's frequently employed on a lot of these tools to give us a feeling for soil types. It is affected by a number of other types of situations in the subsurface, so it by itself is not a straight soil typing tool. Cone penetrometer, again, has been around decades, gives us geotechnical or physical parameters of the soil, what they behave like in terms of stresses and pressure capabilities. Then we get back to, as I mentioned earlier on, very discrete groundwater profiling, very discrete soil sampling, on-site laboratory analysis, either laboratory grade or screening. You can do analysis off-site if appropriate, and then the real-time data management. And we'll talk more about that as an integral part of this system of moving information from the field to the desktop quickly. So there's a quick overview of the types of tools that I would say are readily available in the commercial market today in many countries. I might add that our company uses these from Canada to Mexico down into Latin America and out west to Asia. So these are pretty common tools out there now. This is one way of seeing a configuration. I do this because many times people haven't seen the tools in the field. Essentially, I don't know if you can see my cursor, but you've got a drilling operation of some sort on the left here, and then you've got a sensing van on the right here. I think I can grab a little pen here.
John, do you remember how to get the laser pointer?
How about laser pointer? Whoa. How about we just do a pen?
Oh, there we go.
Yeah, there we go. So any number of types of direct push systems, and I should say most of these direct sensing systems are going to use a push type of, though we have used them in monitoring wells in open boreholes, cone penetrometers, standard drill rigs, but the common use is using direct push tools as it gives us a very high control rate over the pushing. There's going to be some depth detector systems here that link back over to the sensing van. There's going to be some gas lines or fiber optic lines that are kind of running over here. The drill rods themselves are generally brought by the sensing company. Drillers trained. We put some data logging instrumentation under the DPT. And between the two, you've got a coordinated team that can essentially drive these sensors in the ground at full rate. And that drive rate depends on the type of sensor and type of compound or sites that we're looking at. So let's look first at laser-induced fluorescence because we are talking primarily about LNAPLs. Fairly small shipping containers, so they are, you can put them on an airplane, put them on a boat, put them on a barge, whatever you need to do. It's got a excimer-based laser system in here, data acquisition system, signal processing. It's all here. Generally, we're going to push at a pretty constant rate down through the subsurface and collect data about 20 times a foot. The frequency of the laser, again, is such that the polycyclic aromatic hydrocarbons that are in the petroleum will respond with a signature that's unique to that fused benzene ring structure. So we're going to be able to tell the difference between a heating oil or a diesel or a gasoline or an avgas or whatever. So they've all got distinct different, and the system comes with a library of that. Again, this is the thing that everyone needs to know. You have to have the residual phase petroleum in there. So if you don't want to see the dissolved phase, this is a great tool. If you want to see dissolved phase, then you have to supplement it with something like membrane interface growth. So it's great, it's fast, it's accurate in depth, and detection of NAPLs, so we can go through pipelines, retail sites, refineries, storage facilities very quickly and separate out where's the NAPL, where's not the NAPL, and what kind of NAPL it is. They're all tested to a standard reference emitter source. So what that means is if we have a mixture, known mixture of the reference emitter mixture, the system's set to that as a 100% performance before and after every borehole. So when we get a log, like you see here on the right-hand side, that response will be reported in percent of the reference emitted. And the response is going to be primarily driven by the type of compound that's being sensed, and then secondarily by the amount of it, because they're all residual phase materials. So we'll look at some more of these logs here in a few minutes. But you can see here, as we push down, we got a very strong response there and a secondary response here. This zone has a little bit of NAPL in there. We have no NAPL here at all. So very quickly we can take that apart. For the dedicated chemists in the area, on the call, this is essentially we're going to be looking at the PAHs. They have unique signatures. Let's see if I have. So here's the frequency response curves. You can see we're operating, excitation is down here at 308 nanometers, and then this is the decay curve of the response from that. And so the signal processing looks at both the magnitude, the frequency, and the decay characteristics of the curve in order to put it into, we're going to group these into four somewhat arbitrary 50 nanometer wavelength bands. And so the signals that you'll see on the logs that are created will have what we call sort of arbitrary blue, green, orange, and red patterns to them that essentially are those 50 nanometer bands. And so therefore you can look at comparing one band to another. In general, our lighter end PAHs are going to be in the blue-green ranges, and then our heaviers are going to be more over here in the orange-reds. Beautiful thing about the system is it's very linear until it gets way up into the heavy materials, and then that laser light goes into those long chain molecules and basically gets lost and doesn't consistently come back out. But you can see we can operate from over a wide linear range and be fairly consistent. So you know that if we've got more of this stuff in concentration there, we're going to be seeing it. Again, that's a secondary factor to the type of material we're looking at. I think I told you this, but this graphic is pretty critical to going back and sort of smashing that conventional wisdom that LNAPL floats, because here we've got a 90-foot push, and we've got a sort of orangish-greenish typical of a kerosene response at about 20 to 25 feet or so. And then 50 feet below that, we actually have a lighter blue-green response down in here. So we're smearing gasoline down here and diesel up here on the surface. Did that come from this particular source? Not known from this single log, and so we would have to look at these in sort of a systematic approach of looking at the sites. But there's the most clear evidence that I can show you that gasoline does not float because our groundwater table's back up here at 20-something feet. We do see, sort of subtly over here on the right-hand side, that our push rates tend to slow down in where we're seeing that, so that they hit that our push rates were harder or more difficult at those depths, and so we're probably looking at storage materials here. We're looking at tighter grain, harder to push through, though that could be sandy materials, but we've got harder push rates in our materials in those zones. So it gives us a hint that we're looking at storage zones, but based on that information solely, you wouldn't make that call. So that's a quick overview of UVOST, or ultraviolet optical screening tool. And that really kind of is what we're going to use to say, where is the NAPL, both horizontally and vertically? What depths are we dealing at? Okay, so now what we want to know is what's in those pore spaces. What's the water challenge? Because the NAPL is going to compete with the water. So if I've got pore spaces full of water, the NAPL is going to have a higher, essentially what we call throat pressure, in order to move into that pore space. So we're going to have a constant competition going on in the subsurface. If the pore space will take a liquid, who's in there first, and then who's got trying to force their way in? So, how do we start to look at that was really nice when we brought along the hydraulic profiling tool. So I'm going to give you an example. Here's a simple case, and this is going to be hard for you to see, so let me kind of set the stage. So this is a boring log information from the different soil types and descriptions of the site. And you can't see it very well, but our screened interval is sitting right here on our monitoring well. So we're screened over a large number of soil type changes. I think that's a common challenge that we run into in the industry, is we have these long monitoring well screens, but they're bridging across a lot of different transport zones and storage zones. And so this is the result of the most recent sounding of the well. So we've got air down to here. So here's our oil interface. We've got our nice air, oil, and water. So in the well, we have that nice traditional oil floating on water. And so we've got a little bit of water in the bottom of the well and a little bit of LNAPL. Now the problem is this showed up after being clear for many years, and now the atypical call we got was we need to figure out where this oil came from, because we haven't had it for the last 2 or 3 years, and we turned this property over to somebody else and said it was all okay, and now all of a sudden we got oil again. So what's with that? So now we're in the troubleshooting mode. Okay. I'm going to leap a little bit here on you, because this is a membrane interface probe log. So remember, we're looking at volatile organics, and we also have on here the electrical conductivity detector. So this brown line is EC, or electrical conductivity, and this would be indicative typically of larger grain sandy type soils. And so we see that description on the left. We see a larger grain type of response, and we get this nice hump in the curve there. That would indicate tighter grain soils. And I can't really read that description for you right now, but essentially that's what the engineering log is saying, is our soils got tighter or lower resistivity as we did that. Then we come back down and we drop back down around 30 feet. Well, interestingly enough, a heated membrane interface probe did not see much of a signal at all until we got down here right about 30-something feet, and sure enough, that's right where our LNAPL is floating in the adjacent well. Well, that's interesting. So we've got oil underneath the spill zone. This is from a former pipeline. So how did the oil get there to that depth without seeing it sort of move all the way down? We walk back up gradient or towards the anticipated source, and we get very little LIF. Remember, that's going to respond only to residual petroleum. And about 10 to 20 yards back up towards the source, we do get an LIF signal down here at about 31 feet. Fairly weak, very thin. I think that's the other thing I want to point out to you, is these source areas and transport areas and these different geological or stratigraphic changes are very, very thin. But we do see an LIF response down here. And then we we go back and say, well, let's look at the groundwater changes over time. And so this curve that you see kind of going along here is groundwater cycling over a period of time up until about a year and a half ago, and then we had the drought. The drought moved down, and then we started seeing the groundwater or the LNAPL in the well. So here's a classic example where we've got a mixture of residual and dissolved phase product in the subsurface. Take the water out of the picture, let the water level drop, and the NAPL now has room to move into those pore spaces through those throats, and then that's what we see in our wells. ICRC does a great job of case studies of looking at this in multiple conditions. You could have perched water, you could have confined perched LNAPL, confined LNAPL, and this could easily be moving underneath our groundwater table. In this case, we're just moving along the top of the groundwater table. As the pore spaces open up, the LNAPL can move. So there's how we could put together a series of what I like to call multiple lines of evidence. We have information from the well, from the membrane interface probe, from the electrical conductivity, from the laser-induced fluorescence. But actually, we go back to our existing groundwater information, and it tells us a lot about what happened. And so first things I do on a site is try to, what do we already know that we can leverage before we go spend more money out there? Okay. There's another example of the competition. Here's an example where we've got a pipeline corridor here. Pipeline rupture occurs at this location. The conceptual site model of local or regional groundwater direction is believed to be in the white arrow direction. We have our water body over here. Our concern is the pipeline rupture is going to move towards the water body in that direction. Immediate reaction was to install a series of groundwater monitoring wells in the neighborhood, screen them with conventional information, and basically came up with ambiguous or non-existent data regarding the LNAPL. So where did the LNAPL go? Well, we went out with the lasers, which is only going to respond to LNAPL, and we found the LNAPL went the direction of the red arrow. So I ask you, why is that? And again, it's this fundamental concept of LNAPL doesn't move with the groundwater until it, A, gets to the groundwater, B, reaches equilibrium with the groundwater, and then C, the groundwater flows in a consistent direction and can migrate, off of in these transport zones. In this situation, the pipeline rupture was much more shallow than groundwater. The distribution of the NAPL was through the pore spaces that were unimpeded by groundwater. So the LNAPL went north and the groundwater table went left. Once it reaches equilibrium, then the situation will change. But in the early points of a release, groundwater is not going to be the primary contributor to the direction of the LNAPL release. So groundwater is important, but it's not the answer, I guess, is the bottom line there. The other way of looking at this storage and transport issue is if you still have a groundwater problem, low-level groundwater problem on your site, then you still have some sort of residual source. So there's a storage, secondary or primary storage problem that's causing your recurring groundwater levels. Pretty clear that if you remove the source, the groundwater is going to clear out those soils, and we're not going to have any further contamination. But if you've still got back diffusion going on, then there is a source somewhere that's causing that issue. So how can we use this combination of tools to go after that? And the answer to that is not likely going to be in the monitoring wells because of where the vast majority of them are screened today over large intervals that bypass multiple transport and or storage zones, and they're going to be very ambiguous in that information. So what we're going to try to do is go in there and do a diagnostic evaluation of what the site can tell you and what it can't. So we're going to try to go in and look at the source area, isolate that with our, in this case, the laser-induced fluorescence. Let's isolate the source area horizontally and vertically. Let's then bound that to make sure we've got it bounded all the way around. Then let's look at transects, a series of transects across the lines of direction of areas of concern, which could be a number of reasons. It could be property boundaries, it could be water bodies, it could be receptors that we're concerned about. What we're going to try to look across a continuum of a transect and very high resolution for both the contaminant and the soil structure, so we can identify these highways of transport, and then we can go in and target the sampling, target the well construction, screen intervals, heights, and locations, and then target any remedial activity that's going to go on. If we're worried about cutting off the mass flow, we're going to try to identify those very distinct 10% holes in that vertical gradient. And that gives us our discrete samples, and we can confirm what the high-resolution tools are telling us. Okay, so we talked about laser-induced fluorescence for the residual phase petroleum. We've introduced a little bit of the membrane interface probe for the multi-phase volatile organics portion of our LNAPL. Now we're going to talk more about the hydraulic profiling concept. So pretty simple concept. The tools look very similar. We're going to take a source of water at the surface, maintain a positive pressure, a positive flow or consistent flow, and that would be this flow line that you see right here. We're going to maintain consistent flow as we press this tool through the formation, and then we're going to measure pressures. And what we're going to see is things like this, where this little high pressure zone occurs right here, very narrow. Our flow drops to zero, and and then we're also measuring EC as we go down. So we're looking for this very small, in this case, storage zone, and what's the relationship between that storage zone and the LNAPL distribution that we saw with the laser-induced fluorescence. So let's look at some other examples of that. So here's our laser-induced fluorescence log over here. So we might take a site where we've got remediation activities have occurred. We've got recurring dissolved phase concentrations of benzene or whatever that are showing up in monitoring wells. We're trying to find out where are the little pockets of LNAPL left over and what's controlling those. So we might do a lot of screening with LIF, laser-induced fluorescence. This is a signal. We got a pretty good, strong signal of leftover degraded ISPL here. Once we have that map of the NAPL distribution, now we want to go in and say, all right, what in the soils are controlling that? This is the push of the hydraulic profiling tool. We've got a little high pressure point there. But again, we have this very narrow high pressure point right here, resulting in zero flow calculation there, and that zone is right at the base of our LNAPL distribution. So back to our discussion of pore pressure, that NAPL went down until it met a pore that was closed up, and it can't move into that. So those are sealed high-pressure pores that the LNAPL is not able to basically migrate through in that specific location. So we want to get a picture of that on a three-dimensional basis and figure out where's the LNAPL being controlled. Now that could lead to absorption there and then be a secondary source of back diffusion. We don't have that indication here based on the laser. You may want to push a membrane interface probe if you still got how they get from that source over to the monitoring well. Okay, so that's the combination of laser-induced fluorescence for the NAPL with the pore pressures with the hydraulic profiling tool. Let's talk a little bit more about the MIP and look at some of the nuances that come up with this. So, again, simple concept. There is a membrane here. It's surrounded by a heater. I think a little heater blinks here. There's inert gas, typically nitrogen, helium, or air that's coming down from the surface. It's going through a carrier gas line and then back up to the surface, just like a gas chromatograph in the lab. So essentially what we've done is put a membrane extraction system with a purge and trap down here at the bottom of the hole. So we heat the subsurface, I think that, oops, sorry about that. Heat the subsurface to 120 degrees. Typically, we'll do that for 30 to 45 seconds, depending on the type of compound. You want to do that consistently. That protocol per the ASTM is to essentially push for 1 foot, heat the zone for, let's just say 45 seconds, push for 1 foot, heat the zone for 45 seconds. If you do that consistently, then the variability of the subsurface will be the primary factor leading to the data curves that you're looking at. So if heated it, material is, you create a partial pressure there, you've got a lower partial pressure on the other side of the membrane, and so you get basically transport across the membrane from outside to the inside of the inert gases, goes up to the surface, and it sweeps past a series of detectors. Normally use gas chromatographic detectors, so you've got essentially signals coming from things like PID, flammant, FID, halogen-specific detector, XSD, or an ECD, electron capture detector. And so you're able to separate your compounds into different groups of compounds and based on boiling point. Nominal sort of advertised detection levels are like a part per million for fuels, a couple hundred parts per billion for solvents. Today's technology, we're typically operating lower than that. It does have EC on there, as we saw earlier. We almost always are pushing it with hydraulic profiling tool for the obvious reason about the pore spaces. You can put heated trunk lines on this if you've got more difficult weather conditions or you've got other tough types of compounds. I would point out here, as I said, all of these are what we call qualitative instruments. They're helping solve the problem by getting thousands of qualitative data points and really working on the geostatistical challenge. That said, they all have performance test procedures, and they should be performance tests. You ought not be operating with tools that you don't know what their response factors are. So you can have consistent data. They're all operating in what we call a direct sensing or direct contact mode, so you don't have a volume, and therefore you're not going to be able to calculate a mass. So you're not going to get micrograms per liter or micrograms per kilogram. You're going to get a percent reference emitter, or you're going to get a microvolt response off of a detector or something of that sort. They're going to be relative values, and there's going to be a lot of them. So just make sure you understand that. So here's a pretty classic MIP with a hydraulic profiling tool attached, response to an LNAPL in an unsaturated zone. So that's about as textbook as I can get. So here's our PID response. We push down, this is in meters over here, so we're looking at 3.5 meters, we get a response, PID, and its FID partner. That tells me I'm looking at petroleum because my XSD chlorinated detector is just baseline response. So I have a mirror image of PID and FID that tells me we're looking at straight old petroleum responses, and it's occurring from about 3.5 meters, and it's stopping pretty abruptly at 5 meters. So you say, well, why is that? We come over here and look at our hydraulic profiling tool, which is in the same tool rod / string. Here's our flow. We're pushing in a consistent flow fairly down to about this 2.5 meter point. Flow goes to 0. Pressure peaks out. So what am I looking at? Closed pore spaces that are now permeated with this oil, and that shifts again down here at 5 meters. And then I pick up my static water level right there at that point, and then I've got the hydrostatic curve here. It's determined by the dissipation test on the hydraulic profiling tool. So there you have a classic storage zone with petroleum in it sitting on top of my groundwater interface. Now, you don't get that same information out of this EC over here because this would indicate this is larger grain material. So even though we're getting a larger grain material signal on EC, we're seeing very closed pore spaces. So somehow the oil got into those pore spaces. They're now closed. Pressure, there is no real transport going on in there, and that's sitting just above my groundwater interface. Pretty classic response, heated probe, storage zone on top of the water table. And you can see this very quickly, you know, within an hour or two of being on your site, you can start answering the question. Now, if I try to go get that with a monitoring well, it's not going to work for a number of reasons. A, I'm not in the saturated zone of the groundwater region. Second, I'm in a very tight soil, so my mass, this is back to that remedial design characterization. If I want to clear my mass off the site and get rid of this lingering, repetitive groundwater keeps coming up with a very low level amount of material, dissolved phase material, I'm going to have to go after this source, and it's going to be in this tight grain zone. So this is how you can target your dollars in technology and resources as opposed to trying to get the groundwater to give you the answer. So it's just like a sponge. Okay, here's a similar situation. Not an infrequent call, similar to what I talked about earlier. The wells were clean for years. Now the wells have oil in them. Where did the oil come from? Well, so you got oil. We'll start with laser-induced fluorescence because it's only supposed to see oil. We'll go out, push the LIF adjacent to the monitoring well. And just a little backtrack here. This is what the reference emitter test frequency bands look like. You can see the 4 bands there, the blue, green, orange, and red. That's a beautiful, perfect performance test of what we call a call-out there. We have a background check. So here we're up in the 200% reference emitter. Here we're down to less than 1 to 3% reference emitter. So we know we have good, clean signal, good, clean windows, fibers, et cetera, et cetera. Then I push, and I get 2 little bumps right here, one about 17 feet and one about 18, 19 feet. I can pull that data into a specific call-out and look at the frequencies of those, frequency response. You can see the 2 of them look fairly identical, but they look different than this reference emitter up in here. What we're looking at is the magnitude of response, which is low. We're only down 6-7% here. Here it's about 10-12%. And the relationship of the channels to each other. So low blue, a little bit higher green, a little bit higher orange, and then back down to red. That's the same pattern here. So probably the same material, 2 different depth intervals adjacent to the monitoring well. But not much of a response for having oil in the well. So what's the next level of diagnostics or troubleshooting? Let's pull the oil out of the well and see what its signal looks like. So we pull the fresh material, and that's these call-outs that you see here in this zone here. Now you notice they look different. We've got, we do have, let me just back up one for us. Here we've got low blue, higher green, higher orange. Here we've got low blue, high green, but lower orange. So this is a different material, and this one's different than this one down in here. So we've either got degradation going on, meaning the material in the well has lower blues and greens. The lighter ends have been clipped off by the degradation, and the relationships have changed. Here we're talking about 200 or 300% over the other one we were talking about a few percent. So I think what we've got is degraded material. This is obviously fresher. So what's going on? If we then say, well, wait a minute, we know we got oil in the well, we don't have much oil in the formation, what's going on? Well, we bring out the membrane interface probe. Remember, now we're going to heat that zone to 120 degrees centigrade, and we're going to volatilize what's in that formation, and then there's our classic PID-FID signature. So what's happened here is that we had oil mixture in the formation. It got in the well. Our groundwater interface has changed. Our pore pressure relationships have changed, and we're back essentially below saturation concentrations for the oil by displacement, and only by heating it can we pull that petroleum back out of that formation. So we're moving up and down that continuum from saturation to moving on the LNAPL, and we can use these different tools to tell you what stage we're in. And the real key here is probably go back and take a log the monitoring well or the groundwater interface levels over the last months, and we'll get the answer as to when that relationship changed. So there's again, we're using laser for the residual phase or NAPL phase, and we're using a MIP here for the heated volatile phase. So again, the answer is not necessarily in the well. It can be sort of an alert, if you want to call it that, but what's in that well is not necessarily what's in the formation today, and resulting in further site management and remediation answers. Combining MIP and HPT. So I showed you earlier one of these in a classic storage zone of sitting on top of the groundwater. Let's look at it in a little bit different signal. So here we've got a combination of, let's start with the HPT. Let's start with our soils here, and we see our flow. That's kind of an interesting thing that happens here, and then flows tightens up a little bit as we go, or increases a little bit as we go here, and then tightens up down in this zone here at about 5 meters. And it's fairly consistent on the way down, but we do have some divergence going in the zone. Do a dissipation test, and we determine our static water level is about 2.5 meters. And so we know we have groundwater flow regime occurring in this 2.5 to 5 meter zone. Come over here and look at our detectors. We've got a PID response. We've got some FID, what I call smear here, and we're looking at XSD response. So what we really have here is a chlorinated site. Most likely this is a methane off gas, but this is an example of that migration or transport zone that's going on, where we've got permeability here and contaminant as opposed to the storage zone I showed you earlier. Swapped compounds on you, but the point is the same. So I'm going to do a little bit of, someone brings out a membrane interface probe. If you're looking at this data set, let's just make sure you're kind of familiar with the types of things that we're looking at in membrane interface probe. Halogen specific, again, is going to be your chlorinated detector. So here's a 0 to 30 meter response. I've got a lot of variation in the signal, a lot of response in the 10, 12, 15 meter zone, another response here at 18 meters, another response down here at 24 meters. That's XSD by itself. If I add in the PID, I now get a dual detector confirmation that I'm looking at chlorinated compounds. I've got a mirror image each of those peaks. So we know we're looking at a chlorinated compound that has an ionization potential below 10.2 for this particular compound. I add in the FID on that same signal. Now you see I see FID response above as well as below. So here's my confirmation on the FID down in here. So I've got fairly high levels that I can see on all three detectors, but I've also got some FID or flame ionization detector response above this interface here. So most likely we've got a groundwater issue level right here at around 10 meters or so, maybe even shallower, and what we've got is evidence of microbial activity above the groundwater. That's essentially our vapor intrusion question, if you want. It's not a double bonded benzene compound, and it's not a chlorinated compound, so we're most likely looking at methanogenesis. So it's an example of how you can look at groups of compounds off the detector suite. Switch over. Now I've got a PID response, no XSD response here. So now I know I'm looking at double bonds, and I get my FID response to confirm that. So now I know that compound on that side at 20 meters is very definitely a petroleum compound without any chlorinated response. I look at my HPT pressure curve. High pressure, remember, is less permeable. So I got a pressure peak here, pressure peak in here, one up shallow, another one in here. But I got a very definite pressure decrease down in here, more permeable. Is it finer grains? Maybe. That's what this conductivity signal would say, but it's still very permeable compared to the other regions of that vertical boring. I combine that, that's my flow off of that same signal. I combine that back with my PID XSD response. You can see I've got transport in this zone, and I've got storage in this zone. So I have my secondary sources right there. Okay. Back to my friends or enemies, the monitoring wells here. So monitoring wells are great if we get them in the right place, we construct them correctly, we sample them correctly, and they maintain good conditions. Unless you meet all those requirements, then basically the information you get out of the monitoring wells is just misleading. Here's a site that we did after a recent installation of monitoring wells with very short screens, and then we did the direct sensing work after that, which is frankly inverse of what one should do. And here's an example of a discrete monitoring well screen here, and most of my mass is below that screened interval, and a lot of it is down here in we've got a transport zone right there, and a little bit of transport zone up in here, and my monitoring well is monitoring appropriately this transport zone, but not my mass. Second example, here's my monitoring well screen here. Here's my mass here. It's in this storage and transport up here at the shallow. The monitoring well is actually screened down here where it's tighter. It's going to be tougher to get any water out of that well. Another example here, we have a deep, very discrete screen. Here's my mass basically coming from a shallow source all the way down. Here's my permeability zone up here, or my transport zone is up here. Luckily, that's just above where my mass is. So there's an example that we see where it's tight. If a secondary source created, and then this clears out, but our monitoring well is down here, and it's not going to provide the information that we need to effectively design a remediation system. So again, the answer is most likely not in the monitoring wells, particularly if they have any age to them. Okay. I think we just did this one, so I'm going to skip through that. I'm going to log on to the real-time information component of what goes on, I think, is an important element. We use a platform that we created here called Smart Data Solutions. There are other versions of things out there that you can use. What we get with that platform, and which with this tool here, I'm not sure I can show you this, but I encourage you to go to smartdatasolutions.com and sign in for a username and for a demonstration of that. But essentially what we're taking is information from the field, moving it to the desktop on a GIS-based system in a secure cloud platform. So as that boring, like many of the examples that we've looked at so far this afternoon, is created in the field, it is then displayed on the information system, and you have an interactive platform that allows you to look through that vertical depth spectrum, build your own transects that we've been talking about, compare one boring to another boring in terms of relative response, and look at that in relationship to the existing monitoring well or sampling data. So you can pretty quickly off the platform zero in on what depth strata is of concern and what's the extent of the contamination, and what depth zones are they working in, and how is my laboratory monitoring well or sampling information comparing to my direct sensing information. So really, again, just trying to speed up this whole information flow of what's going on. A word of note about, I talked about earlier on where we've got this concept of the LNAPL. It can be below the saturation point. You can reach saturation. You can be mobile and transmissive and recoverable, or you can be even worse than that. You can be moving off my site and causing a problem down gradient or off site. And I shouldn't use the word down gradient. It is quite possible that if I'm not moving and I'm not recoverable, that I'm depleting faster than I am going to be able to be recovered with skimmers and wells, particularly if those wells aren't strained in the right intervals, et cetera. So one of the diagnostic evaluation tools that adds to this LNAPL management issue is what is the off-gassing or the natural degradation state, what's going on. So you can place as many natural source zone detection tools. You can do this. There's probably about 3 or 4 different methods of doing this, but measure essentially the native CO2 versus the CO2 that's being created by the petroleum sources. And there's a couple of different ways of doing that. eFlux has a tool out there. Again, that is generated out of Colorado State research work. And so you can look at what are my degradation rates coming up through the formation and in the source zone compared to not in my uncontaminated zones. And if you've got source depletion rates naturally that exceed those at which you can achieve with your mechanical systems, then you're probably not spending the money wisely on mechanical systems. Case example, petroleum VOCs. Not sure how easy it is to see this, but let me set the stage. Complex facility, lots of storage, our prerequisite water body that's going on down here. These are shots out of the Smart Data Solution System. So I've got a little bit of response up in this zone, up in here. Highest response is down in here, and I'm looking at the total vertical spectrum here, so I'm not isolated, but I'm down to about 20-something meters here. This is that transect view I was referring to here, and this is where you turn on and off your various detectors, PID, XXD, FID, flows, and pressures. So that's sort of the setup of the site. We then put an intersecting transect across the direction of groundwater migration towards the water body in there. This is what that transect looks like on an FID. So coming across at 0 elevation, you can see we've got sort of a couple of different regions of response. So we've got one up here at about 12 meters, another one down about 20-something meters. That one, those can be combined. But you can see we have a changing level in our groundwater, in our detector response. So a monitoring well placed over here at one interval is not going to be the same as a monitoring well placed over here. So we've got across that transect, we have quite a variety or variation in the depth of response on the photoionization detector when heated to 120 degrees. FID confirms what we see, so we know we're looking at petroleum compound. And then if we look at the conductivity, we've got, as expressed by conductivity, tight soils here, a little bit of tight soil here, a little bit of tight soil here, and again here. But what we've got right in here is transport moving across the site based on conductivity only. Is that mobile? Is it transmissive? Is it recoverable? Is it moving? Up there at 10 meters or so, likely not. Deeper, likely yes. Put the pressure curves on there, though, and then you see we got tight pressure, fairly tight pressure here, tight pressure here. Again, varying widely across the site. This is going to be our transport problem right here. So we're going to go screen with our samplers, our monitoring wells, interception trenches, whatever. Those are the depths that we're going to be focused on when we do that. It says the same thing with flow. I should point out that there is a calculation within the software. If we do the dissipation test, determine the static water levels in a couple of different depths in low pressure zones, we can back calculate an estimated K value out of the system. And you can see we have no flow there, but we have fairly consistent flow where we, again, in this transport zone right in here. Is the installed groundwater extraction system, which then went down to about 10 to 12 meters, is that effective? And the answer is no. The petroleum is going underneath the groundwater extraction system towards the formation. So I'm going to kind of stop there, take us back to what our mission is here, is essentially the planet thinking about the data, the information, the structure of the soils, permeability, the distribution of the contaminants, what one system will tell us versus another, and looking at multiple lines of evidence. So I'm going to kind of stop there. And, you know, I don't know, Jackie, whether you have plans for questions, but I'm certainly available to take a few.
Yeah, so if everyone sees the chat box there on the right-hand side, if you want to go ahead and use that to enter any questions you have for John. Also, if you could let me know if you're watching the webinar today with other people, and let me know how many people are watching with you. That way I can get an accurate account for today's attendance. John, I'll just give them, you know, a minute or so to type out their questions.
Right, and we certainly can make sure, Jackie, they can certainly email in or Skype in or link in or anything else if they have questions afterwards too. So.
Perfect. And I will email everyone once we get off here with John's contact information as well as a link to a survey.
That'd be great. It's an easy crowd you got.
All right, we have a question here. Greg, I'm going to unmute your line. Are you there? Greg?
What's the average cost for a transect or two?
Yeah, good question. You know, how complex is your site? I didn't cover costs, but I'm glad you brought that question up. So these tools, you know, in the hands of the providers within the United States are typically going out, you know, if you combine the drill rig with the tools and the data processing, you're typically looking at, I'm going to use a term like $4,000 to $5,000 a day. If we're looking at laser and HPT tools, which are really the primary ones for LNAPL, you're going to knock out, let's say, about 300 feet a day, 250 to 350 feet a day. So if you got 30-foot borings, you're going to get about 10 borings down. So, you know, that's a good day. That's a couple of transects probably. So you're looking at a couple of 30-foot transects in a day, depending on all the other issues, traffic, soils, coordination, et cetera, et cetera. MIP is slower by, and I think everybody can tell me the answer, you have that heating cycle in the MIP. If you're true to the MIP tool, you will heat consistently across your data set, in which case you can add, you almost cut your production time by about 40% by the time you put that heating cycle in there. A lot of the production is just moving boring to boring, so just a lot of that interference. Hopefully that answers out. Okay, one question online here, Jackie. can you tell the difference between heating oil and diesel with LIF? And the answer is yes. Obviously, if they're both fresh, it's easier. If they're both degraded, it's harder. Maybe you supplement selected locations with the MIP, which will separate out compounds a little bit more on the PID there. So if you've got any volatile components, you could separate it out that way. But there is a definite signature difference between those two products.
Okay, great. Thank you. I just had those two questions, so I think we're all set. Once again, when you close out of your webinar, it will directly send you to the evaluation, but I will also send that via email and John's contact information. And hold up, John, we do have one more question. What is the applicability of these technologies on fractured bedrock?
Oh, the new frontier, fractured bedrock. So, again, these are direct push tools, so fractured bedrock generally is not very receptive to it without a borehole opening prior to that. So if you're looking at deep borings into fractured bedrock and you've got boreholes cut, we can lower probes into there. I would think that would be more of a membrane interface probe type of world, or maybe HPT. You could also use a combination of packers to pack off zones if appropriate. I would say that's a bit of a new frontier that hasn't been explored very well much yet. We have done some of that work, and I would say the lessons learned are still out there. The laser being a tool that's going to go look for LNAPL itself. If you can't get it through the formation and there's not a LNAPL there, it's probably not going to see it. All of the tools have some degree of sensitivity to subsurface conditions in terms of both matrix effects, just like the lab does, but also damage if you slice membranes or scar up your sapphire windows or whatever. Then you're going to have a little bit of replacement time or downtime in there, so we tend to carry lots of backups and multiple strings in order to keep the production up. So when you're talking about a specific site, make sure you talk through with your vendors that what kind of material you're going to run into: cherts, bedrocks, fractured bedrocks, sharp phase granites or whatever, so that you can put some planning time into how to deal with those situations.
Oh, so we have one more question. What QA methods do you use with these tools?
Good question. So quality assurance starts with a few basic fundamental concepts. One is equipment configurations need to be standardized so that length of cables, flow rates. So there are set points or lineup configurations that need to be adhered to and documented. The software has actually logged those configurations, so as they come through the data processing, we grab that. You also have remember I talked about the response testing. Just like every qualitative instrument, there is a response test that should be performed. Our protocols to do that before and after every boring, because we've been in those, that sort of tough formations down there. We want to know that we've got the proper data acquisition from the window all the way back through the data acquisition system. So there is a performance test. You must achieve a certain response based on a known standard that the system is exposed to. Obviously, there are checks within the software itself. It's checking to see whether you maintain flows in the case of the MIP, maintain frequencies, and so there are interlocks in the data acquisition that give you alerts if your system's not operating correctly. And then we have two other lines of evidence here at Columbia. We're using a degreed geochemist in the field to observe that data, so we're looking at the response of the instruments versus the formation of the chemicals that we're expecting. So are you getting what you expected from the instruments based on the knowledge of geochemistry that you have? And then the next layer is when it comes into our data process, and we've got a backup person here on this end that's reviewing all the logs that come in. So we've got a lot of real-time QA going on, and it's really boring by boring quality assurance. The reference is, then a good high-resolution sampling program to go together on the end of the project is always a very useful tool to compare, what we get out of soil results or water results based, and how does that correlate back to the direct sensing information. So it's usually, and we recommend, a multiple lines of evidence type of approach.
All right, we have Ruben, are you there? Ruben, do you have a question?
Yeah, my question is, what are the challenges with this kind of technology, if there's any?
A few things that I would caution you on. Obviously, the first we've talked about is drilling conditions. So that's an important component. So where can we push these tools and where can we not push these tools? You can put them waterborne. You can put them, in odd locations. So I'm not really worried about that. Competing compounds are always an interesting challenge. So knowing what you know about the site as best as possible. If it's not what I call sort of the standard 6 or bad actors out there, then we would usually do what we call bench testing to make sure we can verify performance of the system for each individual chemical, and then any interference you may get from one to another. So other chemicals can be both a blessing and a curse, because you can have interference from compounds for your primary compound of interest, but you might also have good surrogates or indicators of your compound of interest. So you could use a volatile organic. I think one of my favorites where we use TCE to track tritium on a DOE site. So it's kind of an interesting challenge. Membrane interface probe is bringing up a very saturated vapor stream from the subsurface. HPT is obviously water, so when you're in this time of the year in the northern hemisphere, you get down into freezing conditions with wind chills. Special procedures need to go in place, or you may just not want to do the project when you've got particularly freezing conditions out there, because if you get ice flows or blockages in the line, that can cause some issues. By the same point, if you breach the membrane or get a water slug in the system, anybody that's operated a handheld PID knows that you can get a false positive. We use a set of water traps and dryers in the system to try to minimize any chance for that. We're always on the lookout for that, but you need to make sure that you're getting consistent, repeatable data. I think that's another lesson learned for any qualitative instrument. Is the data repeatable, depth-wise, compound-wise, pressure-wise, whatever, and how does that compare to what the formation should be telling me? So there you go.
Okay, great. We have a question from West that he would like to ask via phone. West, if you would enter right into your keypad on your phone the star, that 9XX number that you sent me, and then the pound, that will link your phone to your name so I can unmute you. You need to hit the star first, and you can do that at any time into your phone. And then, Ronald, I unmuted you. Do you have a question for John? Oh, Ronald, are you there?
Oh, yes. Yeah, my question was, after you do all the field work and you collect the data, what do you actually give to the consultants? Do you interpret the data yourself, or is that an extra charge?
Yeah, we here use what we call a level 1 and a level 2 report. So as we are collecting the data on our Smart Data Solutions site, a real-time report is being generated. So it's a description of the instruments, detector principles of operation, and then the actual data itself. So you're getting the data, essentially the data report, log by log in real time off the website. If there's an interest in interpretation of the data, where's transport, where's permeability, where you have likely storage zones, those types of things, then we have a team that does what we call a level 2 report, and it does have a higher upcharge for that because they're going to be spending, time comparing your existing versus wells and things of that sort. And the end result is a fairly comprehensive deliverable that tells the story as updated with this data collection effort.
Okay, good. Thank you.
Yeah.
Okay, we have a couple other questions that came in via the chat. Can the software use the Transdec data to generate a fence diagram or a 3D representation?
The acquisition software does not do that. Smart Data Solutions has some Transdec capability in there that you can snapshot off. All of the providers, I think, will give you the actual raw data files coming off of the systems. Ours are downloadable right off the website, and they can be put into a myriad of other software tools to do transects or fence diagrams, frequently done, but that's, again, sort of an upcharge because that's not a standard part of the process. It's really kind of client by client or site by site as to what's useful and what data you want displayed in the fence. Do you want the monitoring wells in or not? That type of question. So that's the kind of thing we'd like to cover in what we call a joint scope of work when we're setting a project up. If you want that, who's going to do it? You're going to do it. We're going to do it. We need a third party to do it, or what way to handle that kind of question. But yes, it can be done. It's very, very rich data in terms of resolution. I would caution anybody that's doing data visualization, fence diagrams, three-dimensionals. I think I showed you enough examples of the discreteness of the data. So I take you back to that LIF picture where we had diesel up at 20 feet and we had gasoline at 90 feet, 70, 80, 90 feet. Last thing you want to do is put that into a smoothing, kriging, three-dimensional, whatever way you want to use it, and smooth all that data, because now you're going to show a distribution of product, between 20 and 70 feet, which just doesn't exist. So you have to be very cognizant of your data regimes, so to speak, and don't blindly smooth data into three-dimensional, what I call potatoes in space. So be careful about that.
Okay, I have a question.
You spend a lot of money to get discrete data. Don't smooth it all out.
All right, I have a question here from Kevin. If your project already has wells and source zone removal, but high VOCs remain in down gradient water wells, is one justified in going to this parallel full assessment?
To me, that's one of the best use of the tools. It's really what I call a diagnostic evaluation. If that's the situation, why do we still have the problem? So where you either have one of two issues. One, we haven't got the source zones identified, or B, we don't have all the transport zones identified, and the down gradient wells are not monitoring the right depth intervals. So I think it's an excellent use of the tools, and it's typical of a lot of the projects that we get into. How did it get in my neighborhood, so to speak?
Okay, we have a question here from West. I apologize, wasn't able to unmute him. I can't find his phone. He did type it in. He says, I understand that many states are using MIP instead of LIS. LIF response, because of this dependence of PAH constituents, may not be reflective of the actual mass percent.
True. I'm not aware of a lot of states using MIF instead of LIF. There is a lot of MIF work that's done out there. There's a lot of LIF work done. So I think it's a perceptive question. If you're looking for the residual mass of PAHs, the LIF is going to be your better tool for delineating that. If you want hints and distribution of where that is, some look at vapor intrusion issues, and you might want to look at dissolved phase, then your MIF is going to be a good backup tool. The way we cover that is we carry both. So if we're doing an LNAPL site, we will start with the LIF until the LNAPL PAH residual distribution is mapped. Then, in consultation with the technical team, decide, well, do we want to look at any further distribution of dissolved phase below saturation levels or any vapor issues, in which case we will then shift to MIF. So I don't think it's an either or, and therefore applying the right technology.
All right, thank you, John. That was our last question. Thank you again for taking the time to present with us. For those attendees still on the line, again, I apologize for all the technical difficulties we had in the beginning, and thank you so much for staying with us. I will be sending out an email here very shortly to all of you with a link to the survey and also John's contact information if you have any follow-up questions. Also, when you close out of your webinar today, it will automatically take you to the survey. So if you could just please fill that out, we'd greatly appreciate it. Thank you so much, everyone.
Yes, thanks to everyone for attending. I appreciate it.
Bye.